off when we finish the quiz doing the 4-4 introduction. And I just realized I have your quizzes here. I didn't need to show those to you, so remind me at some point. Okay, so in each of these, we just practice taking the derivatives. Notice it's with respect to time. So everything is something dt. Okay? I'm going to start on 10. I'm going to go out of order. Just because we're jumping back in midstream, 10 would be an easier one to jump back in midstream than number 8. Yep. So, perimeter of a square, P equals 4S. What are you thinking?
dp dt.
Derivative of P is just going to be dP dt equals derivative of 4S. 4 times
dp dt.
ds dt.
Oh, that's what you do.
Because this is kind of like when we did implicit differentiation. Okay, you're taking the derivative, so the derivative of 4s is 4, and then it's just times the derivative of s, with the derivative of s is the change in s, the change in t, so ds dt. Okay? They're all in, because remember, it is all in respect to time. Okay? Let's go backwards. Let's do 9. Area of a circle.
D of A over D of T.
Okay, derivative of A, dA dt, the change in A, is equal to, what's the derivative of pi r squared?
2 pi r.
Yeah.
2 pi r
dr dt.
times dr tt times the derivative of radius with respect to time. Okay, that takes us back to 8. Okay, we got our warm-ups in. What's the catch with 8?
There's RA and H.
There's an R and an H, so we're going to have to think product rule, okay, which is what we did with number 5 with length and width. Okay, now there's a couple different ways we can do this. First of all, derivative of S.
ds over dt.
ds dt. Now, one option, this is what I was debating of how I want to show this. One option is, okay, what do we know about the r is a variable, the h is a variable. What about 2 pi? It's just a constant, yes?
Yes.
So one option we could do, this is what I have in my notes, is just keep the 2 pi, and then I'm going to do parentheses or bracket. I don't know why I have a bracket here, but parentheses, bracket, whatever. And then do the product rule on the RH. So which way do you guys want to start this? Derivative of R is 1. Keep the H. And then don't forget, times, derivative of R is 1, but then times what?
dr dt.
dr dt.
Yes.
We just usually put that out back. So H dr dt, that's product rule, so plus. And now?
H. Or, yeah. R dh dt.
Okay, so we're going to keep the R. Derivative of H is 1, and then times dh dt. And you could leave your answer like that. Okay? If you would have like just assigned the 2 pi to kind of do with the R, you just have a 2 pi on each term. Okay? What about 11?
dB over dt. Oh, wait. The same thing, like pi.
Yeah. Could we put the pi out front? You can. If we're just keeping the constant of pi out front and then taking the derivative of r squared h, there's not a 2 pi. So then, what are we doing? The derivative of r squared is 2r. Keep the h and dr dt plus, this time what are we doing? Keeping the r squared And the derivative of h is
1 dH.
1 dH dt. So in my notes, I have it written that you could have it like that, or you could have the pi multiplied in. So you could have like a 2 pi RH here and a pi r squared here. That would be an option as well. Okay, what about 12?
Well, same thing.
Could you take the constant out front if you want? Yeah, constant that's going out front is the 1/3 pi, which I just wrote 1/3 pi. I just looked at my notes. 1/3 pi, keep in mind, is the same as pi over 3. I'm not saying 1/3 pi is wrong. I'm just saying more typical in calculus is that you might see pi over 3. Okay, and then you're doing the derivative of the r squared h again. Didn't we just do this?
Yes.
Yeah. Derivative of r squared is 2r, keeping the h, times dr dt, plus, this time I'm going to keep the r squared, derivative of h is 1 dH dt. Okay, 13. Volume of a sphere. Derivative of v is going to be dv dt.
This one.
Can we do 4/3 times 3?
I would. Because, I mean, that 4/3 pi, you can think of just sitting there. But then when you do the derivative of r cubed, it's going to become 3r squared. So that 3 times 4/3, yes, I would go ahead and definitely multiply those. 3 times 4/3 is going to make it 4 pi r squared. Are we okay? 4 pi r squared times dr dt. The change in r with respect to time. And lastly, this last one's not bad. Side lengths of a triangle. X squared plus y squared equals 25. Derivative of x squared?
Oh,
2x times
dx dt.
the change in x over t with respect to t, so dx dt, so 2x ddt, 2x dx dt plus derivative of y squared, 2y dy dt equals the derivative of 25.
0.
0. Okay. I have written in my notes, and we'll talk about it, but when we start talking about sliding ladders, we often talk about Pythagorean theorem here, and that's what you're seeing there. So, okay, guys, that was some introduction there of looking at just how to differentiate these formulas, because that's one of the things you're going to have to do, is you're going to have a formula to connect to the problem, and you're going to have to differentiate it, okay? Now, okay, just some information to go through, okay? The derivative, dy dx, of a function y equals f of x is its instantaneous rate of change with respect to the variable x. We've talked about IROC before, right? When a function describes either position or distance, its rate of change is interpreted as velocity. So anytime we talk motion here, we start talking velocity. In general, a time rate of change answers the question, how fast is a quantity changing? For example, if it is volume that is changing in time, then dv dt is the rate, or how fast is the volume changing with respect to time? Those are the types of questions will be asked, is how fast is something changing? If a person walking towards a street lamp at a constant rate of 3 feet per second, then we know that distance is decreasing. So if x is your distance, dx dt, the change in distance, is negative 3 feet per second. And that is the matter of the distance between the street lamp, how much it's decreasing. If they walk away from the lamp, the distance is increasing because your distance is getting bigger and the rate of change becomes positive. So those are different scenarios that we'll talk about. Now, we have kind of 5 steps. I don't think I usually really number them. She kind of numbers 1, 2, 3 a little bit that we'll talk about. I don't necessarily number them, but these are kind of some of the pieces. Okay. When we're solving relative rates problems, these are a big deal in calculus. One thing, make a sketch. Okay. Sketch out the scenario, whatever it might be, assuming you can. Label all the quantities. Okay. Read the problem and identify all quantities as known, given, and find with the appropriate information. So basically, I kind of go through and I look at everything in the problem. What do we know? What are they asking us to find? What's given? Put labels with all of that. Just kind of get everything organized here. Okay. 3, write an equation that involves the variables whose rate of change either given or are to be determined. All these types of equations that we just saw on the other page, not what we found, but the ones given. You know, like we just saw Pythagorean theorem, we saw some area, some volume formulas. Those are some of the different formulas you might be using, okay, to connect everything. Then, this is what we just practiced doing, use the chain rule, implicitly differentiate both sides of the equation with respect to time. So that's what we were just doing, taking the derivatives. And then after completing step 4, it's substitute into the resulting equation all known values for the variables and their rates of change and solve for whatever you're asked to find. Okay? So I'm going to work you through that process. Number 1 isn't exactly related rates problem. It's kind of getting us into it. But starting with 2, we'll talk about some related rates problems and what we can do. Okay? Let's look at 1 here. Okay. Suppose x and y are both differentiable functions of t and are related by the equation y equals x squared minus 3x. They're asking us to find dy dt when x equals 3, given that dx dt equals 2 when x equals 3. Okay? So, nice thing, they give us an equation, yes? Okay? So, we don't have to, it's not a matter of, what equation. We don't have to figure that out yet. So we're going to be using the equation y equals x squared minus 3x. Notice they're asking us to find dy dt when x equals 3 and when dx dt equals 2. Okay, and again, that is specifically when x equals 3. That's all the information they're giving us. Now, first thing we've got to do, they're asking us to find dy dt. So we need to take the derivative of both sides with respect to time, because they're asking us to find dy dt. So, just like what we were doing on the other page, what's the derivative of y? Dy dt, right? Because officially it's 1, but then with respect to time, that's that chain rule, so we say dy dt. Okay, keep going. What's the derivative of x squared?
2x.
Okay, 2x, and then times the chain rule, dx dt. Minus, what's the derivative of 3x?
3 dx.
Okay, 3, then times the chain rule, dx dt. Now, our job is to find dy dt. Do we have all the information we need?
Yeah.
Technically, yeah, we do. Okay. It's solving at this point. If you want to, you could factor out a dx dt. I'm not sure it's necessary, though. Okay. I mean, you could, it's your choice. You could, before you get started, rewrite this as dy dt equals, and say 2x minus 3 in parentheses times dx dt. typically you see the dx dt part at the back. I'm not saying you have to do that. I'm just saying that's another way to write it. Okay? We have all the information we need. Solve. Okay? So we're being asked to find dy dt. And I'm going to use the evaluation bar and say when x equals 3, because that is what they asked me to do. Okay, find dy dt when x equals 3. Plug it all in. Are you guys using the first one or the second one?
First.
First? Okay. So 2x dx dt. 2 times what is x?
3.
3 times what is dx dt?
2.
2. Minus 3 times dx dt. So 3 times 2. Do the math.
6.
So dy dt when x equals 3 is equivalent to 6. Okay, that's very basic, but that's kind of the gist of what we're going to do. We're just going to be more in a word problem scenario. They're not going to give us the equation. They're just going to give us the piece of information, and we need to go with it. Okay? So, are we ready to talk about this next one? A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay. Reread it a couple times as you need to, right? What kind of information do we see here? Okay. Which, by the way, do you guys have the visual of what's going on here?
Yeah.
It's what they say. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So what are concentric circles? You've got your pebble and then...
Small, bigger, like a solar system.
Okay, but there's the idea of concentric circles, right? I don't have the exact definition for you, but you have the idea, right? It's that the rippling effect there. Okay, so there's our picture. Not that there's really much I need to label on the picture, but okay, what can you pick up from here? What were you guys picking up? I heard you.
It's increasing at a constant rate of 1 foot per second.
Okay, increasing at a constant rate of 1 foot per second. What is it?
The outer ring ripple.
How about the radius of the outer ring ripple thing? However he said it there, right?
Yeah.
Okay, so the radius is increasing at a constant rate. We're talking about the change in radius per time. So what they're giving you is dr dt. They're always going to give you some kind of information like that. You just have to be able to identify it. It's a change in r over time. And that change in r over time is what? 1 foot per second, yes? And notice it, in my brain it's logical. The change in radius over the change in time. A radius could be labeled as feet. Time could be labeled in seconds. So it's change in radius over time. Okay. What else? What are they asking us to find?
When the radius is 4 feet.
When the radius is 4 feet, What do they want?
The rate of the total area.
Yeah, total area. Yeah, I guess the whole thing. I could underline the whole thing, can't I, here? But, okay. When the radius at 4 feet, at what rate is the total area changing? So what are they asking us to find? The, not just area, but the change in the area? How am I going to write the change in area? They're asking me to find dA over dt when what? When the radius is 4. Okay, are you with me there?
Yeah.
I'm just trying to identify everything. Now, in the no part, that what she usually puts in that part is what's the formula that connects all this? We have our given information here. We know what we need to find. What formula are we looking for here? What equation? What are we talking about?
Area of a circle.
Area of a circle. What's the area of a circle formula?
It's pi sometime.
Pi r squared.
Actually, yeah.
Not able to find the exact area. Can't find the exact area.
Augie had the deer in the headlight look of, oh, I gotta know that formula now.
Yeah.
Okay, so we know the area formula. It involves radius. And here's your clue, guys. We're given dr dt. We have to find dA dt. Does this formula involve a and r? It does. Okay. So we're going to take that formula. A equals pi r squared. And our job is to differentiate it. Okay. So the derivative of A is dA dt. Derivative of pi r squared. 2 pi r times dr dt. Okay. Okay. So, okay, let's look at what we know and what we're being asked to find. We're being asked to find dA dt, yes? Okay. So we're being asked to find what's on the left, dA dt. 2 is 2, pi is pi. Do we know r?
Yeah.
It asks us to find it when r equals 4. dr dt, do we know dr dt?
1 per second.
Can we plug it all in?
Yes.
dr dt is 1, r equals 4. We can plug all of that in.
Who can do it?
Okay, so we're going to substitute. I don't know if you necessarily want to write this down or not, but we're going to substitute in that dr dt equals 1 and r equals 4. And we're going to do some math. So, dA dt equals 2, which is 2, pi, which is pi, r, what did we say r was?
4.
They told us to find this at when r equals 4. dr dt we identified to be 1. What is 2 pi times 4 times 1? 8 pi. I guess realize dA dt when r equals 4. I should have put that up on the previous line too, but 8 pi. And you can leave it at it's 8 pi unless for some reason they want a decimal. What about labeling?
8 pi feet per second.
Change feet for radius.
Okay. It's change in area over change in time that we're finding, right? What is area labeled as?
Feet squared.
Feet squared. What is time?
Seconds. Feet second. Feet squared per second. Squared.
So feet squared per second. Now, I didn't do it up here, but if you go back in 2 pi was 2 pi. 4 was 4 feet, yes? And what was this 1? It was 1 foot per second. If you multiply those labels, does that give you feet squared per second? And it does. Okay, guys. That was your related rates problem intro. That to me is a true related rates problem. Okay?
I think I have to do that. Maybe. I will see.
The key is there's easy ones, there's hard ones. So,
Sometimes I don't know what they're on.
this is an easy one. Okay. Okay, ready to talk about a balloon?
Yeah.
And I don't know if I exactly followed them in the exact order, but basically I did her guidelines for solving 5 related rates problems. I did basically all 5 of those. Okay. Pretty much in the right order, too. Okay. Air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon changing at the instant the radius is 30 centimeters? As you reread it, start dissecting. What are they giving us? What are we finding? What formula do we have to consider? What is this whole problem talking about when they're talking about air being pumped into a balloon?
Volume.
Did you guys catch that? They never used the word volume, did they?
They use cubic centimeters.
Okay, but it's air being pumped into a balloon. Okay, and cubic centimeters, that's always my clue also. But air being pumped into, this is indeed a volume problem. Okay. Got anything you want to identify, or what do you want to tell me?
Yes. I got you. For the given, it would be dA over dt, I think, equals 800 cubic centimeters per minute.
dV over dt.
I said one tiny mistake.
No.
Why would I use dV over dt?
Cubic centimeters.
Because we're talking about the change in volume. Why was it dA dt last time? Because we were talking about the change in the area of the circle. Okay? So, dV dt, the air is being pumped in, is changing at a rate of 800 cubic centimeters per minute. Okay, good, good. Our know is the formula we're going to be talking about, and the find, what are we going to have to find?
The find is the
The what?
dr over dt.
How fast is the radius of the balloon changing
At
dt
r equals
at the instant the radius is 30 centimeters? Okay. So we need a formula that's going to connect. Basically, I see volume and radius. We're talking about volume of a balloon, of a spherical balloon.
volume of the sphere.
Volume of a sphere.
Oh gosh.
I don't know.
Are we? We're gonna have to know this
Pi r
stuff.
cubed. That was a guess.
2 pi r squared.
What?
3,
4 over 3.
4,
Boom.
Yeah.
Okay, so volume, yes, your volume formula is it's r cubed, right? And it is 4/3 pi r cubed.
Do we get like a cheat sheet on the AP test or not?
I agree. Can you give us the
They
equation?
did on the
You do not.
SAT.
You do not get a cheat sheet of anything.
But on your test.
Would, gosh, I don't know. Would they give you a formula like this?
They usually do.
Sometimes, I will say, if there's a formula that is pertinent to the problem, I do feel like that they will give it to you to an extent. Now, would they give you this one, though, or expect you to know it? I don't know. The more you know, the better off you could be. Okay, you guys ready to start?
Like jug.
Well, we can't plug yet.
Oh yeah.
Why not?
Because we get a DV.
4/3 pi r cubed, volume equals, we don't have a dv dt, a dr dt, we have to differentiate. That's always a step here. So derivative of v, dv dt. Derivative of 4/3 pi r cubed.
4 pi r squared.
And I don't know if you guys have realized it or not. Were most of these formulas we've already done on the previous page?
Yeah.
They are. Could you go back and use that page? You could, but do you also need to know how to do it in the moment? Yes. Okay, these formulas should all be seeming familiar to you. Okay, let's check. We're given dv dt. 4 and pi are numbers. It's asking us to find when r is 30, and we're finding dr dt. Is everything covered?
Yes.
We either know it or we're being asked to find it, yes?
Yep.
Okay, so now in my notes I worked this with labels. Should I work this with labels to, I don't know. Okay, dv dt was 800 equals 4 times pi times r squared times dr dt. Okay, well, I don't know, what is 30 squared?
900.
900 times 4.
9 times 4, yeah.
So right here I have
3,600.
3,600 pi times dr dt. That's equal to the 800. And I'm not saying you can't use calculators. I'm just trying to get you to use your brains here, okay?
Wait.
And then how do we solve for dr dt? You're doing 800 divided by 3,600 pi. Now,
Wait, how are you finding?
Wait, come on, that does something. Right.
That's not right.
yeah, wait. Are we okay with what I've done or no?
Yeah, I'm trying to figure
I'm trying to get dr dt by itself.
Okay.
So I divided 3,600 pi over to here. So, and I just 800 divided by 3,600 pi, yes?
Oh.
Now, the obvious I see without grabbing a calculator is those zeros, right? Top and bottom both divide by 100. I need to look at my answer key to see how they express the answer. So now I'm at 8 over 36 pi. Those both divide by 4. 2 over 9 pi. And that's honestly how the answer is in my book. Now, thoughts on label. What were we being asked to find?
DRDT when R is 30.
dr dt. So the change in r over the change in t. What's our radius label? Radius is measured in centimeters. What's time labeled in? Minutes. So this is centimeters per minute. And note that is 2 over 9 pi. Okay? That math wasn't horrible. And as I said, some of these I do have a calculator happening. Some of them I do not, so. Okay, you ready to talk about 4? Yes, no?
Yeah. Just stand up.
Why? I should be tired.
Okay. The top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? here becomes the importance of a picture. Okay? This is the importance of a picture because, and it's also a typical calc related rates problem. Okay? The sliding ladder down the wall. So, the top of a 25-foot ladder is sliding down a vertical wall. So, there's my wall. There's the ground. There's my ladder. What did I just draw?
The triangle.
A triangle, specifically a
Right.
right triangle. So here is my wall, in case you were questioning. Here is my ladder. And obviously, the ground is the ground, okay? The top of a 25-foot ladder. Does that ladder change at all? No. That ladder is 25 foot throughout the whole problem. It's not going to change. If it's not going to change, you can go ahead and label that in your diagram. Okay? It's going to be 25 foot. I don't need to use a variable for the ladder. It is. Yeah, the ladder's sliding down. But the ladder's always going to be 25 foot.
Yeah.
Okay. Now, it's sliding down the vertical wall at a constant rate of 3 feet per minute. So what you're looking at here, what's the ladder is what? It's sliding down the wall. Maybe I don't need my line quite that long, but it's sliding down the wall, yes, at a constant rate of 3 feet per minute. Now, be wary of the word when, because it says when the top of the ladder is 7 feet from the ground. Is the top of the ladder always 7 feet from the ground?
No.
No. Do not label this side as 7. Okay? It's only going to be 7 when we put that value in to find our answer. Am I making sense here?
Yeah.
Like, we don't want to put it, make it 7 the whole problem. It's not 7 right now. It's when the top of the ladder is 7 feet from the ground. What are they asking us to find? What is the rate of change of the distance between the bottom of the ladder and the wall? So what are they asking us to find here? The bottom of the ladder, the distance between the bottom of the ladder and the wall. So now we're looking at, as my ladder scoots farther to the right, as the bottom scoots farther to the right, we're being asked to find that change. Does that make sense?
Yeah.
Okay. So I have a wrong label in my notes, and it was really confused me. Okay, so on the no, what's my formula going to be?
Oh. A squared plus B squared plus C squared.
Okay. Generally speaking, a squared plus b squared equals c squared, yes. Now, I'm probably going to use x and y, and instead of c, what do we know? That ladder, it's always 25, yes? It's not like the 7 that is a changing amount. And so I have mine listed as x squared plus y squared equals 25 squared.
Can we put in at either the x or the y? Can we go ahead and put in 7?
No.
That's where we'll take the value.
We cannot put in 7 until we go to find it, because you can't put in the 7 to differentiate, or it'll mess things up when you differentiate. Now, with this in mind, obviously one of these sides is x, one of these sides is y. We need to decide and go with it. What I will say is, more often than not, you end up with x being the horizontal piece and y being the vertical piece. I'm not saying it has to be that, but more often than not, that's what you end up with. Okay? So, with that in mind, what's my given information?
Sliding down the wall on a constant rate of 3 feet.
Okay, and what is that? if this side is y, that 3 feet per minute slide is the change in y over time. So dy dt. Now, which way is this ladder going? It's going in a negative direction, so this is negative 3 feet per minute. Okay. What are we being asked to find?
X over dt.
We're being asked to find the rate of change of the distance between the bottom of the ladder and the wall. So that is going to be the change in x, dx dt, when
Y equals 7.
when the top of the ladder is 7 feet from the ground. So thus, y equals 7. Technically, it's 7 feet. Okay, I think we have everything to proceed. Okay, take your equation. X squared plus y squared equals 25 squared, and differentiate. Derivative of x squared, 2x times dx dt plus the derivative of y squared, 2y dy dt equals derivative of 25 or 25 squared is 0. Okay. And at this point, you will see, so on the last one I did, what did we do? We plugged the values in and then solved it, yes? What you will also sometimes see is, what are we trying to find? Dx dt. So you will sometimes see, instead of plugging stuff in, going ahead and solving for dx dt. Both are good. I've seen it taught both ways. I personally think it depends on the problem. I'm not going to argue that you should always do what we did last time and plug in and then solve. I'm also not going to argue that you should always not do that. So if we're going to be solving for dx dt, I'm going to solve this one. So if I'm going to solve this, I'm going to keep 2x dx dt. I'm going to subtract over 2y dy dt. How do I solve for dx dt? Divide by 2x. Now, when you divide by 2x, we can write this as negative 2y divided by 2x, and then still times dy dt. If you want, what can make life a little bit better? Could the 2's cancel? Yeah. So then you've got the negative of y over x dy dt. Okay, well, let's see what we can do with plugging in. So dx dt, we're trying to evaluate when what? Y equals 7. So it's going to be the what? Negative of y, so 7, over x, times dx dt, or excuse me, times dy dt. So times negative 3. What is x?
X is
25.
20.
No, you do a squared plus b squared equals c squared with the 7.
If this is 25,
That's 7.
y is 7,
I have no idea.
you have to find it. Okay, so this is one of those problems where we hit this point, it's like, oh, we're missing a piece of information we have to go back and find. Now we can use the 7 because I need to know what is x at the moment y is 7. Okay, so x squared plus 49 equals 625. Because I know that 25 squared is 625. 625 minus 49 is 576. And that leads x to be 24. And again, it's because I know some of those bigger squares. So what are we doing over here? Now we're putting 24 in. So yes, that's an added step sometimes. Sometimes you have to go find a piece of information that we didn't know. So dx dt, when y equals 7, what are you cleaning that up to be? What'd he say?
Negative 21 24.
I disagree.
Positive?
I could go with positive.
Oh, yeah.
Negative times negative is positive.
Whoopsie.
I also know that 21 and 24 both divide by 3.
Which was 7 over 8. That's 7.
Now, if it's a multiple choice question, you need to find the 7 over 8, right? If it's a free response, could you have stopped at 21 over 24? Most definitely. Okay. 7 over 8 what?
Feet per second.
Feet per
Feet
minute.
squared.
Feet.
Per minute.
Feet. Something for the feet. Just feet.
How about feet per minute?
Sure.
Because it's dx dt, so the change in x, what was x? X was a length, yes? And then time was in minutes here.
Oh, brown time.
Can we look at the quiz?
Oh, yeah. I got 1, 2, 3, 4, 5 to do one.
Although I'm going to go back through and compare with homework and decide if we're going to do them all or not.
Oh, we
Okay.
got plenty of time.
Not really. I'm short. I need
Oh.
6 days in this school week to make things work well in here, and it's not going to happen. So,
We're coming out Saturday.
okay.
No.
Here's what I will say is that we are. I don't think I want to get into this problem really. So, it's a big one. So,
Doesn't look that big.
yeah, it is.
It's only 1 2
It's noon, a shift.
Okay.
East.
We are. This is a good stopping point. So I am going to call it a stopping point, and I'm going to let you look at your quizzes.